From Epifanio Virga.
Well, thank you, John, very much for your introduction, and I'll thank the organizers at the end, just for a change, as Carl did. And I would like just to set the scene of what I'm trying to do in this, present in this lecture. It is essentially a twofold attempt. I will, on one side, try and build a mathematical model which describes the behavior of nematic shells on one side, and on the other side, of course, this such a step has many pitfalls, of course, and one has to be exposed to criticism. Well, there are a number of assumptions I'll make, and of course, I'll take both friendly and unfriendly questions on this part. Concerning my second goal, which is interwoven with the first, would be to, on the way along the construction of such a model, I would like to keep rather general level of understanding. So I will not specify too much the energies and the functionals I'll be concerned with, but my attempt will be primarily to identify a number of predictors. The main objective is to find a number of simple predictors that would indicate where defects are going to preferably lie or be located on a nematic shell. So, I'll try to combine these two goals, and because one influences the other. All right, what a nematic shell is, it has been already recalled, and we can give different representations and different representations of the system. I'll try with very simple-minded models, and then I'll also go and construct something which is presumably more realistic, but unfortunately, at the same time, a bit also more complicated. So the first take is to imagine a surface which bounds a colloidal particle and which has been decorated with a thin film of nematic liquid crystal. And this is a dream that David Nelson started to dream in 2002, and I think we still dream it, and would be the idea of using these constructs to build the basis of a new chemistry, which is this metamaterial chemistry. In such a chemistry, essentially, atoms and molecules are replaced by nanoparticles and by colloidal particles. And the idea, of course, is that nematic defects will play, which decorates the surface, as I said a minute ago, will play a fundamental role in locating the points where ligands would be attached, and so they could bridge one particle to another. So the idea is that the number of molecules, the number of defects, of these hot spots on the surface of the colloidal particle, are going to play the role of the valency. And so this is the new chemistry in which you number and you count the number of defects on the surface, and you assign the ability of the particle to be bound to other particles in the system. All right, as I said, my attempt would be to build a three-dimensional layer around these particles which possesses a two-dimensional order. So this is a slightly more complicated picture I have in mind, and I'll try to construct it bit by bit in the sequel. But just to start and just to get started, there is one simple approach to this field, which has been followed by many people already, and it is just to imagine in a purely, genuinely two-dimensional picture, to imagine that there is a director oriented on the surface which bounds the colloidal particle and which is bound, for whatever reason, to stay always tangent to the surface. So my only assumption on the surface throughout the talk will be that the surface S is closed and orientable. And this field N is going to be the director field. We have seen these pictures already in this workshop, showing that the sources are somehow limited. And as I said, David Nelson started dreaming these dreams for us, but we keep dreaming it. And I've just singled out a sort of beginning and temporary end of this history. And of course, I have deliberately ignored plenty of intermediate contribution to the field. Now I need to go to the traditional stick because my advanced one is not working. And of course, we have already been reminded about this fundamental Poincare theorem that says that since I have a number of defects on the surface, a topological charge assigned to each of them is denoted by mi, and the sum of all these topological charges must be equal to the total Euler characteristic of the surface, and it is related to the genius, which is related to the genius G of the surface itself. And here is a kind of dichotomy, and which is phrased in the language of chemistry in a way. I'm saying, well, this ball is either divalent or tetravalent, meaning it has 2 defects or 4 defects on it. Of course, both answers to this question would be perfectly compatible with the topological constraint, provided, of course, in the first case, both antipodal defects have +1 charge, and in the other case, all defects have charge +1/2. All right, depending on the model you adopt, both answers could be correct, and depending also on the specific situation you are envisaging, both answers can be correct. Of course, what is my goal, as I said, and I'm bound to repeat it, my goal is to imagine to have some simple, and I stress simple, predictive criteria that would indicate, which of course wouldn't work in this case because the sphere is the easiest and also the most symmetric situation you can imagine. But imagine for a moment that the surface is not as simple as a sphere. My goal is to construct criteria that would at least indicate where defects are more likely to arise and where defects are less likely to arise. So let us go to the mathematical model. This is just suffices for my introduction. And so if we look into more details into the microscopic structure of this layer, which covers the colloidal surface, one might think of little ribbons, these molecules which lie on the surface and are free to glide on it. Well, this is again a little bit too naive because there is not such a thing as a single layer of molecules sitting on the surface. So the least you can do is just to imagine that the surface itself is producing an anchoring field which is diluted in space, and such anchoring field is such that orients all molecules in a thin film wherever on the tangent plane to the surface. Tangent, of course, meaning it is a local tangent plane which is parallel inside the layer to the real tangent plane to the surface. So this is going to be my language. As I said, S is the closed orientable surface on which all my discussion will be based. Little l is a unit vector which designates the direction of the long axis of this biaxial molecule, and nu is going to be the outer unit normal to the surface, and this is a constraint which I will apply throughout the layer. All right, I need to introduce a kind of descriptor of the order inside the layer, and I can do essentially two things. This is a thin three-dimensional layer on top of this surface, and one way to do is to imagine this as ordered in space. If I imagine this as ordered in space, then I take the usual second moment distribution, and in which the ensemble average now has to be considered and meant to be done across the layer, and I subtract to it the isotropic measure of the isotropic second moment. So, and this, how can I identify the isotropic second moment to be subtracted from the second moment distribution of molecular vectors? Well, it has to obey, just by symmetry, this property. It has to be invariant under all rotations, which means that being completely isotropic and being attached to the isotropic distribution within the layer, and so it has to possess this property, and since its trace is 1, as 1 is a trace of the second moment distribution, there is only one answer to this requirement, and we know this, of course, already from Desgen, and so this would be the appropriate measure on the, of the order inside the layer. But I could do something else, because there is a kind of, the surface is imprinted into the layer through the assumption that all these molecules, though freely moving, are bound to be parallel to the local tangent plane. And so I could say, all right, if I now envisage this as a two-dimensional system, I subtract a transversally isotropic measure of order, and so I need to construct, again based on purely symmetry arguments, I need to subtract the most general second moment tensor, which of course now obeys a different symmetry property. It has to be invariant under all rotations that preserve the normal. And this, of course, would qualify the local order, or actually the local absolute absence of order on the surface. And again, if I impose these constraints, which derive from the property of L to be everywhere orthogonal to the normal layer, this is the unique answer I get. It is 1/2 the projector on the surface. So these are two different measures of order. One is the order in space, the other is the order on the surface. But of course, this second moment is the same. So it means that if I eliminate this second moment distribution between these two expressions, I get a relationship between the three-dimensional measure of order and the two-dimensional measure of order. And of course, they are related, as it is clear from here. And of course, this means that if the system is disordered on the surface, meaning that QS is 0, stands for surface in this case, well, Q is different from 0, and indeed this means that molecules are, on average, distributed parallel to the tangent plane. And if the tangent plane well, the tangent plane, we'll see in a moment, if the tangent plane varies from point to point, this, of course, will introduce a further distortion into the picture. And it can easily be shown as well that this two-dimensional measure of order annihilates everywhere the normal. So now, what is the most general? Of course, I have some, there is no reason to prefer one to the other, to these two measures. They are related via this geometric quantity. But of course, everybody has preferences, and I'm no exception, so I'll prefer this second measure of order, and I will phrase my theory in terms of it. It is possible to show, it is simple to show that given all these constraints, QS is represented by this expression, and so it has one nematic director, so to say, a scalar order parameter which will play a role in a moment, and the orthogonal director and perp, and it is easily seen that this is a purely biaxial, a fully biaxial tensor if seen from the perspective of a three-dimensional system. All right, this means that a defect occurs now wherever in this two-dimensional picture, whenever lambda vanishes, which means, of course, that QS vanishes, and this order parameter lambda is bound to live in between 0 and 1 of. All right, what I need to do now to construct an elastic energy, starting from my order descriptor. And my point is, and this is again one of the assumptions of the model, that both these tensors can be viewed as fields on S, on the surface. And not only I assume this, but I also assume that the measure of local distortion is given by the surface gradient of this tensor. And there are arguments, which I will not dwell on at this stage, which support such a choice. And in particular, of course, I'll refer to this simulation work by Selinger and co-workers on tori, where they actually started from a simple interaction, kind of modified Mayer-Zaupe interaction potential, and they proved actually that a measure of distortion for the energy is a surface gradient instead of the covariant gradient of Q. This is a matter of choice, which can be debated, as I said, but it will have such a choice, it will have consequences on the further development of the theory. All right, and I need to keep in mind that I could always extend both these fields, Q and QS, in particular Q, out of the surface, and if I do such an extension, at least locally, I am guaranteed that the normal gradient of this field is 0, and so this makes me happy to use this elastic energy for three-dimensional nematic systems, which has been proposed long ago as a general expression for the Landau, for the distortion in the Landau theory. And now, of course, these L1, L2, and L3 are not the original constants in the paper that I mentioned, but these constants must play a role of phenomenological constants in my theory, and I hope to be able in the future to provide a microscopic argument which, starting from this energy in the layer, would produce the appropriate expression. Yes?
Yeah,
sure, whatever. I said already. I take both type of questions.
On the ds, how you define it in plane or not, is it trying to get the difference between, for example, if I take a cylinder and I align stuff along the axis, or I align it along
yes.
the radii, if I use only covariant derivative, you don't distinguish.
Yes.
And you want to distinguish between the two, so that choice will guarantee coupling to the extrinsic curve. Is that the...
That's a perfectly, this is a concise way. Yes, I try to be more conscientious than that, because this will have consequences on, but if you were to give the lecture, yes, you would have spared 15 minutes by saying this. No, that's correct. I like this. This is perfectly correct. This is precisely what I'm trying to do, but I'm trying to do it in a, so to say, in a systematic way, starting from, I would say, first principles, but from other principles in a way. It is, I think that this is an issue which could be tackled in different ways. I'm not saying that this is the most original or most appropriate way of tackling it, but the construction of the two-dimensional theory out of a three-dimensional vision of the layer is a question. I'm not saying that this is the best answer, but this is one way of doing it. Thank you anyway. All right, so I have this machinery here, and this is a little bit technical, but these are the most general invariants. But as you see now, already phrased in terms of the surface gradient. And the reason is that in this theory, the normal gradient is 0. So I'm just taking the typical Longa-Monzelesan-Trebin approach, and I am applying it to my layer with the further assumption, which is justified by my model, that normal derivative of this tensor is 0. Now, and this is what Vincenzo said a minute ago. The moment I relate the surface gradients of these two guys, of course, I get a curvature contribution coming from the other guy. And you see from here, I get my elastic energy density as a nice structure. I'll come in a moment to explain what this F sub s is, but you see these curvature terms are automatically produced by this difference. And these are the terms that make a difference in a cylinder between the two arrangements that Vincenzo was referring to. Of course, there are these extra terms, which I will drop in a moment, because for me the surface is given a fixed rigid. So these will play no role in my minimization process. But if I were to consider a vesicle, a deformable vesicle, you see that my elastic model immediately produces terms which are of the form of Frisch energy, essentially. All right, what is this F sub s? F sub s is just the version of the Landau-Degen theory, but phrased in terms of this surface invariants. These are precisely the same invariants that occur in the general three-dimensional theory, but now they are phrased in terms of the surface gradients of my surface two-dimensional order tensor. And of course, this is well known. All right, there is a null Lagrangian in this picture, and the null Lagrangian comes from the fact that though these two surface terms, densities, iota S3 and iota S2, are independent algebraically from one another, their integrals over any closed surface is not independent. So it means that if I compute this difference, I get something which is the integral of the Gaussian curvature times the trace of Qs squared. This was essentially my lambda squared, and so we'll see in a moment that this geometric term will interfere with the Landau potential, because the Landau potential is a polynomial in lambda. And actually this will interfere with a quadratic term, which is the only one that depends on temperature. So in a way, this would introduce a kind of geometric dependent temperature. It is a kind of rescaling of the transition temperature given by geometry. All right, and then I rephrase my energy by collecting all non-trivial geometric terms which have been generated in the two ways I have indicated, and now I combine this with the Landau-Degen potential, and I play the same trick. I usually start from my three-dimensional version of the Landau-Degen potential. I use that relationship between Q and Qs. Of course, this, as I said, is a quadratic term which has a coefficient depending on temperature. Usually this little t, which will enter later on, is the reduced temperature. And I express now the invariance of Q in terms of the variance of Qs. And no surprise, of course, that there is no cubic term in Qs, because the trace of Qs is identically 0. So this means that eventually I can rephrase the three-dimensional Landau potential in terms of this two-dimensional Landau potential, in which, of course, there is no cubic term. And this means that in 2 dimensions, also on a surface, of course, the ordering phase transition is second order. But again, we need to keep in mind that this is not alone, because this term will be complemented by the Gaussian dependent term. All right, now the point is, in 3D, everybody knows what the undistorted state is. Just imagine that there's a gradient of Q, the 3D Q in a 3D sample is uniform. This translates the idea that all molecules are happy in a nematic when they are aligned in one direction, and this direction is whatever you want. You have this degeneracy. But what is the notion of indistorted state which is appropriate on my setting? And how shall I formalize it? Of course, in this case, the undistorted state and the ground state coincide. There is no energy associated with no distortion. That's the idea of elasticity. But what happens in our case? Well, in our case, QS is given this form. And of course, the first idea is I take lambda uniform. It is a scalar. It is the same everywhere. So it is a good thing to imagine that an undistorted state, whatever it is, possesses uniform lambda. But can I devise the correct notion of absence of distortion for n and n perp? Well, of course, it is enough that I construct a concept of undistortionness for n, because n perp being orthogonal to it will be undistorted as a consequence. So I'm down to identify the notion of lack of distortion for a unit vector field on a surface. It's a very simple problem. All right, the first idea is to say, all right, I take the surface gradient of n identically 0, and I'm happy. But it's wrong. It is wrong because due to this constraint, if I differentiate on the surface, I get this relationship within the curvature tensor as a surface gradient of n. So if I impose this, this will entail that n is an eigenvector of the curvature tensor with 0 eigenvalue. And so it means that I cannot choose n as I wish. So this means that the undistorted state is not identified by taking the surface gradient of QS identically 0. What shall I do? Well, what emerges out of it, by the structure of the energy that I have already derived, what emerges out of it is that whatever I do, whatever notion I introduce for the lack of distortion, it will entail some energy. Because the energy, Fs, is a quadratic form, and so if I'm not at liberty of taking surface gradient of n identically 0, some energy will be attached to it. Whatever I choose as a measure of lackness, of lack of distortion. So this means that I need a notion of lack of distortion, but it also means that I need a name for this energy which emerges. And I've chosen this fossil energy. I don't know whether fossil. I think is it fossil or fossil? Fossil. All right. Could be, well, whatever you like. But all right. Also, this means that the local ground state will have no 0 energy. But of course, this is not in general a big concern, because you always think of rescaling the energy and making it 0, but this is not here. It's not possible because this fossil energy will depend on the point on the surface. So it is a field on the surface. All right, just to make a long story short, this is the idea of introducing a distortless unit field. Well, it goes back. You simply introduce a chart. You introduce a frame. You have seen this already many times, and there is no need for me to dwell into more details. And the idea is, of course, the simple, oldest idea of Levi-Civita of parallel transport. You introduce this frame, and a frame that wanders on the surface. It is called the Levi-Civita frame if its spin vector lies on the plane tangent to the surface, which actually can be also characterized in terms, in variational terms, to be the frame with the least spin in which the director hand is seen to be immobile. Anyway, I don't think I need to go into more details. One way, a technical way, is to introduce a spin connection, which has been already evoked more than once in this workshop. You imagine a curve with tangent t and with arc length s. And if you imagine a map, a chart there with u and u perp being the unit vectors normal tangent to the coordinate lines, this is the way to translate mathematically the parallel transport property. But you can do more. This was the spin connection was the way to transport parallel to itself a unit vector. Now the question that you ask, if you want to identify an undistorted state, would be to say, suppose that I assign n at will, which will be the kind of quote-unquote surface gradient of such a field that would, at each point and in all directions, perform the parallel transport of that vector. So this is the same notion, but applied to this faked surface gradient, which is, and of course, correspondingly, the surface gradient of Q will be different from 0, and this is the answer. So you pick up any unit vector, and this is the way to transport it parallel to itself in all directions. So you assign a surface, a faked surface gradient. It is faked because there is no guarantee that this field can be extended to the whole surface, being the gradient everywhere of a unit vector field. This is just a local argument that can be done on a small patch, but can be done on every patch. And now your request is you have identified, by the way, this is precisely what makes the difference between the surface gradient of n and the covariant gradient of n that already featured in Luca's lecture. Of course, it has been derived in a different way, and it has been assigned a different meaning, but you can always prove that the surface gradient of n is a covariant gradient of n, which featured before, plus this tiny bit. And this tiny bit is precisely responsible for the transport of the n field. All right, then you just do what the great before me have done. So you go back to Erikson's inequality, and you ask yourself, what would be now the expression of Erikson's inequality? First of all, you need to phrase them. The way to phrase them is to require that whatever surface gradient of QS you take different from this fossil one, you get an increase in energy. So that this is really the ground state with non-zero energy. And the answer turns out to be very simple. These two inequalities must be positive. Of course, these are far less complicated than the same inequalities that have been already worked out in the three-dimensional case. And the reason is that, of course, less distortions are possible in this two-dimensional setting. In particular, I would like to draw your attention to the fact that as a consequence of these two inequalities, the third one is valid, and this will play a role in a moment. All right, my time is running, and so the idea now is precisely based on this fossil energy. And this fossil energy, which has not been inserted ad hoc, but which has been unleashed by the system itself, by the surface itself, will play the role of some predictors, will indicate in which direction some predictors of the presence or absence of defects has to be thought. All right, so I simply now rewrite, this is just formal, I simply extract the fossil energy. It is just a matter of algebra, and this, of course, will be the fossil contribution coming from this approach, so that at the end of the day, you write the total, the fossil free energy density as a combination of these two terms, and you see immediately that this term, which was already generated by the first reduction that we performed, as guaranteed to have a positive coefficient, pre-coefficient, and so it means precisely that the energy is always penalized by a positive constant times that term. All right, we simply decompose the surface gradient of mu into this normal form. Sigma 1 and sigma 2 as the principal curvatures, E1 and E2 the principal directions of curvature, and of course H and K are the mean and the Gaussian curvature. And we write the local measure of alignment in this frame, in the frame of the principal curvature. And then we, after some algebra, we simply rewrite our fossil energy as a sum of two contributions. And in this these two contributions are different in nature because one does not depend on the relative orientation of the nematic director with respect to the basis of the principal directions, theta here, as the angle that the director makes with one of the principal directions chosen at will, and the other does depend on it. So, just a matter of semantics, we say that this is an order potential because it could influence only the order in terms of the curvatures, and this is an alignment potential because it looks like a kind of localized electric field that would be minimized in one or another of the possible configurations for the director depending on the curvatures. And this is going to be our major player, and once written in the local basis of principal curvatures, it acquires this formula, and it immediately reveals that there is one special case in which this term is completely meaningless, and it is when sigma 1 is equal to sigma 2, because which are the umbilical points of the surface. On the umbilical points of the surface, this aligning potential is null, and of course this means that the curvature by itself doesn't know in which direction the director has to be oriented. But of course the problem is to minimize it in the general case. So we call W naught the cosine of 2 theta naught, we call it the minimizer of this, and there are several cases. For example, it is easy this is a quadratic form, it is immediate to prove that if this combination is non-positive, then only two possibilities arise, namely W naught is plus or minus 1. The plus 1 means orientation along the sigma 1, the E1 direction, minus 1 means orientation along the orthogonal direction E2, because this is the cos of twice the orientation angle. On the other hand, you could, if this combination is positive and you are away from an umbilical point, which is critical, as I said, then this is the explicit expression of the minimizer and could be either in between minus 1 or 1. If it isn't, then you need to look for the minima of this expression in the extrema, so it would be either plus 1 or minus 1. So we come to the attractor criterion, and the attractor criterion say that in general, this is a general statement, you might expect lines or points on the surface on which this W naught is discontinuous. This, for example, is a case of a torus. You can prove for a torus, if you go back to this expression, on a torus for which this combination is 0, L2 plus L3 is 0, which is possible according to the Erikson's inequalities, then you easily prove from here that if sigma 1 plus sigma 2 is equal to 0, namely if there are lines along which the mean curvature is 0, and on a torus, it is a very simple exercise, it is possible to play around with the anisotropy of the torus to find the two symmetric lines in which the total curvature vanishes. Of course, there are always two lines on which the Gaussian curvature line vanishes, but here we are interested in the mean curvature. If this is the case, then you can prove that on one side of the torus, the preferred alignment is along meridians, and on the other side of this line, the alignment preferred by this potential is orthogonal to the meridians. which means that along these lines, defect can be generated. Actually, these lines could play the role of defect attractors. So this is my time is really running out, but this is a general scheme. What we do, we simply study, as I said, umbilical points are always there. We simply study the geography of these W0 minimizers on the surface, and sometimes it is surprising. All right, the order potential is much easier to tackle, and what actually we found interesting is another criterion which has to do with the repulsion of defects. Defects can be attracted, and I just gave 2 glimpses of how the defect attractors can be located on the surface, but they can also be repelled. Of course, they are repelled whenever order prevails, and the way to identify where and how order prevails is to construct this potential, which is a minimum of the previous potential plus the order potential, and ask yourself whether or not such a potential is minimized on the surface, because wherever it is minimized, order is preferred. If order is preferred, defects are unwelcome, and so they are repelled. So now, at the end of the day, at the end of the morning session, this is the point. We have 2 criteria: criteria for attractor, defect attractors, the criteria for defect repulsion, and we try to apply them. And the easiest application is on an ellipsoidal shell of, right, this is the ellipsoidal, this is a cross-section of the ellipsoid we are considering, which is symmetric and rotation about this vertical axis. A is the semi-axis along the z-axis, B is the semi-axis in the direction orthogonal to it. And this is the case I would like to show. It's the only case I will show. It is a case in which L1 is given by this expression, and L2 and L3 are equal. In this situation, what happens, this is a theta naught map. Theta naught is the cosine of theta naught is a W naught. And if you look at the lower folder, this applies for prolate ellipsoids, where A is greater than B. And you see what happens. There is a zone along the equator in which there is a preferred orientation of theta naught, which is neither 0 nor pi over 2. And then this preferred angle goes to 0 at the poles. So it means that our orienting potential actually wants the director to be oriented at some angle with the meridians on this equatorial zone. And this actually is a plot of W, and V is the coordinate that runs from pole to pole along the meridian. And you see from here that this is a conclusion. The minima of this potential, the one that detects the repulsion, are at the poles, meaning that these defects tend to be repelled from the poles. I didn't mention, but the attraction defect in this case is void, because the only points that in which it would apply are the poles, where no which are umbilical points for the ellipsoid, and so there is no preferred direction there. And this, of course, goes hand in hand with this other criterion, which says that, which is prevailing actually, and which says that defects have to be are repelled by the poles. All right, how do we test these predictions? This is a prediction for the oblate ellipsoid. The minimum here, as you see, is rather picked around the equator, and so you conclude that qualitatively these defects are repelled away from the equator. And of course, a numerical solution of the Euler-Lagrange equations associated to this functional actually shows that for prolate ellipsoids, defects actually are repelled by the poles. And this is a profile of the order parameter. And you see, indeed, the profile of the order parameter increases near the poles, which makes, of course, hard for the defects to reach them. And of course, again, this is just based on a numerical relaxation of the total free energy, including all the terms that I have seen. And this would be the Mercator map of the director field. And you see, actually, these are the 4 defects. All of them have 1/2 disclination, 1/2 charge. And you see these are bent or twisted in the language of Vincenzo. So this is what happens for the prolate, the oblate ellipsoid. We knew already that equator here would repel defects, and indeed it does. Defects are lingering away from the equator, and indeed on the equator there is a rather robust increase of order which acts as a barrier for the defects. All right, so I think I'm done, and I need just to put on the last slide and to thank my co-workers and the support of the Newton Institute. But if you allow me just a few seconds, I would like to express my gratitude to the organizers of the program, of the liquid crystal program, because they have really made a wonderful job. And I think they've been able to not only organize a good series of meetings and workshops, but they've made the atmosphere and the scientific environment in the Institute quite pleasant. And I think that they've proved experimentally that good science can be done in friendship. And this, I think, makes science itself maybe the most enjoyable and the highest of human endeavors. So thank you to John, to Mark, to Misha, to David for your tremendous work. Thank you.
Thank you, Epifanio. Maybe just a couple of very quick questions. I was looking for people who are not asking questions usually. I'm going to interrupt.
So much of what you said applies not only to nematics, but to, say, a vector order parameter. But there's one aspect to this theory that's different, namely that the curvature induces order. So if I started off with a sphere and converted it into an ellipsoid, I would necessarily have pneumatic order present. And so that, if you thought about that problem of how the curvature would induce an order throughout the sample.
No, this is actually something that we should look at, because just changing the geometry and driving the order on the surface. Thank you.
No, but it's related in a sense. There was a comment that you made that sounded really interesting. You said that the transition temperature, you can see from your formalism, will depend on curvature. Can you expand it? It was too concise for me to understand in detail.
Yeah, because if you write down the condensation energy, which has this Landau-de Gennes potential, which is inherited from the layer, and it is quadratic, of course, in lambda. But then the elastic energy via that identity, the null Lagrangian, produces another term, which is quadratic in lambda, but it is multiplied by the Gaussian.
Right, so practically, if I give you a surface that's both positive and negative Gaussian curvature, and you have an island of the isotropic phase, and
yes.
I want to, the isotropic phase everywhere, where do you nucleate first the nematic?
Yes.
Where? This is a question. Where?
This is a
positive,
question.
Negative, God knows.
No, well.
Well, you know, actually, because you have
Yeah, I know,
in
because I have the expression, and I simply add this K, which, as I said, renormalizes the transition temperature. And so since there is a minus T into the A parameter plus this K, if K is positive, it reduces the temperature and vice versa. I mean, you need to do the algebra right, but it is just a difference. It is a shift.
Yeah, no, but it's position dependent.
The shift is position dependent.
We're running into
It's a wonderful talk, Epifanio. So the element of introducing a free boundary would perhaps permit simpler ground states, because right now you've got an imposed geometry that's causing geometric frustration.
Yes.
So if you relax the constraint and allow it to be a free boundary, then it would become purely topologically driven.
Right.
That's the question.
Yes. It goes in the same direction as Tom's remark. This has to be done. I mean, of course, if one believes in such a derivation, and I think we had a chat with Dasha Jumer, and he agrees that we should really do some work and have a kind of molecular argument that derives these L's from first principles, because these are similar, they are akin to the usual L's, but they are not just the same, and I'm not so convinced that you get those L's by multiplying by the thickness of the layer the three-dimensional ones. There should be something. I think this is too simplistic to be true.
Last two questions.
Thank you. So do you have the cubic term which is proportional to the curvature, which then vanishes on the flat curvature?
I have the quadratic term, which is
The cubic in Q.
cubic in Q.
Yes, and proportional to the curvature, so that on the flat surface you have second-order transition,
Right.
but on the not any other surface, the transition may be still first-order.
Right. Correct. Correct.
Lunchtime. Thank you very much.
Thank you.